Asus best.
I want to sample.
Okay, so at the last lecture we were talking about making pipes and talked about seamless and high frequency welded pipes, and I just started to say something about lined or clad pipes where you're trying to put a corrosion resistant alloy of some sort, could be nickel alloy, could be stainless steel, inside a much cheaper and more substantial, generally, carbon steel pipe. And you can either do that by cladding a material onto a sheet, so rolling together the corrosion resistant alloy and the carbon steel, and then forming it into a pipe and welding it in the similar way that we have seen earlier for a simple carbon steel strip. Or if you can make a tube that you can slot into the hole in a larger carbon steel pipe, you can make that process without having to weld. So these could be seamless tubes that you could put together, or they could be welded tubes. It's easier with seamless tubes because you've got no weld sticking out on the top to get in the way. Now often the way this is done is to heat the carbon steel pipe up so that it expands, to insert a cold liner pipe, and then allow the cooling to take place so that it contracts and bonds onto the surface. But there's no metallurgical bond in these cases, it's just usually a simple mechanical bond. You can then, during the hydro test, pressurize the inside, and you can expand and plastically deform both, and you may get a metallurgical bond after that point, but it isn't essential. So if the inner liner is breached, you may get some interfacial penetration of your gas or your liquid that's in the pipe, and that can lead to corrosion problems and other things. But it is something which can be done, at least on relatively short lengths of pipe, quite straightforwardly. It's quite difficult to put 12 metres of tube inside another 12 metres of tube, but in 1 metre or 2 metre sections it's relatively straightforward. So this is more likely to happen in special parts of refineries, or perhaps in areas around valve assemblies and things where you need extra corrosion protection. So when you've got a clad pipe, you may want to seal things because you don't want the gas or the liquid to get in at the end of where the cladding actually is. So if you imagine here is the carbon steel pipe here. Here is the liner. It sticks out a little bit beyond there. You can put multiple welding passes here to seal it so there's no gas path to go through that internal gap. Maybe you don't need to do that much. Maybe you only need to put a single pass to seal it here. And then the liner, this is a stainless steel filler which is being used effectively, or a nickel chrome alloy filler which is being used for the alloy pipe, but there's only one pass, it's not a multiple pass weld. Now when you've got lined pipe, if you bend the pipe, the liner can move with respect to the outside. If it's clad, then the liner is fixed. And this means they behave differently. If you try and make a small diameter pipe and then reel it up on a reel barge, you will find that the reeling process, where you coil the pipe up, is very different if you've got clad pipe and if you've got just lined pipe. So with these mechanically lined pipe systems, they don't reel very well. You could imagine that as you bend the pipe, it's easy to buckle the inner liner away from the main part of the system. So you bend the pipe and the inner liner collapses and buckles away, and you get large void spaces at the interface, which can be problematic for gas entrapment and for corrosion. That generally means you have to have larger radii of curvature when you reel them up to avoid that from happening. So it's not impossible to reel these systems, it's just difficult. So we have had some use of clad pipe. The BP Rum gas field development had quite a high amount of CO2 and sulfur, and an 8-inch carbon steel pipe was internally clad with stainless steel, and 25 chrome, so that's a ferritic stainless steel. And it was just used for the export manifold line from the subsea manifold to the Bruce processing platform. Now that sounds great, you know, you've got a pipe coming up, and it's where we're taking it from the seabed to processing platform where other things are happening to the gas. It's a relatively short length of pipe, just depends on how deep the system is. And it can be cost effective to do that. The pipe that went from the processing platform to shore was not a corrosion resistant alloy lined pipe, it was just an ordinary pipe. So some of the processing was done on the rig to actually reduce effectively the CO2 content of this system. Now the interesting part about this also was that 8-inch pipe was built into a 14-inch carbon steel pipe, so we had a very complicated pipe within a pipe construction, and that's because there were worries about forming hydrates, methane hydrates in the system. So the pipe was an insulator for temperature, and it actually had some umbilicals going down there with electronics and heaters and things. So the pipe itself that was laid was not just the delivery pipe, it was the complete pipe necessary to do all the things that had to happen in that effectively riser situation. And the main role of the outside carbon steel pipe is mechanical protection. So it was accepted that there might well be some corrosion of that pipe by any seawater leaks and things, but that wasn't its main function. So what I wanted to say really about pipe manufacture was the traditional, most common manufacturing method, submerged arc welding, large diameter, high pressure pipelines, and that's been used for a long time and still is used today. But spiral pipe has also started to become more common because of the quality improvements and the reductions in cost. And if you want to buy longer segments of pipe, the spiral process is available. So we talk about standard 12 or 18 meter lengths for pipes. If you're buying 18 meters, it's easier to do that with a spiral pipe than it is for the longitudinal welded pipe. 12 meters is probably the longitudinal weld that you'll get. And cutting down the number of on-site welds by using longer segments of pipe is one of the cost calculations that you have to do when you're working at the cost of manufacture. So for offshore applications, that's probably more likely to pick longer lengths of pipe. For onshore applications, you're more worried about being able to deliver things to site. The shorter lengths of pipe are used. So there's a lot of factors, not anything to do with the basic material or the basic pipe manufacture, that you have to take into consideration when you're ordering these pipe elements. Seamless pipe has been used traditionally for small diameters, particularly when the pressures are high. But increasingly high frequency welded systems are being used because, again, improvements in quality of the manufacture and reductions in cost. Seamless pipe by the piercing method is expensive because you've got to do the processing hot, so the processing equipment is expensive for you to be actually to do that. Corrosion-resistant alloy pipes can be produced by any of the processes that can produce carbon steel pipes. The welding parameters and procedures are different, but the processes are exactly the same. So the process isn't the limitation, it's merely the cost of the alloy. And that's why we have a tendency to use clad pipe, either mechanically lined or metallurgically bonded rolled, because that's cheaper. Corrosion-resistant alloys, as I mentioned before, may be as much as 16 times the cost of the carbon steel pipe. And that means that if you've got a very long pipe run, the materials costs will become too much. Whereas if you clad a carbon steel pipe, or you use a lined metallurgically bonded system, you can save money and still have that high corrosion resistance. But then you have to deal with the fact that you've got a two material hybrid system. It doesn't behave quite so simply. Now there are some developments in pipe manufacture. Sometimes you can take a steel pipe and increase the pressure that it can withstand by winding composites around the outside of the steel pipe. So this is a composite reinforced line pipe, CRLP. So effectively you can see the process here. The steel is wrapped with glass fibre composite, and you're almost using the composite as your corrosion protection layer as well, because you don't have to paint these in quite the same way. And this is particularly good if you want to increase the risk of long propagating failures, because you've got almost like a compressive winding around the outside. I'm told, and I can't say anything other than what I was told, that it saves in welding time and it can save in costs overall for these very large diameter pipes. I have no direct evidence that that is true, but it is one of those things that people say. So what you can do basically by saving welding time is use a thinner steel pipe, so less welds have to be put in, and then you make up the strength by the composite around the outside. So that's why it saves welding time. It's not that there are less segments welded together. Exactly the same number of segments are welded together. It's just the thickness of the pipe is less. So you save on the time of welding that way around. 4 to 12% overall saving. Composite material is more expensive, but it's not that much more expensive than the steel pipes. So it's probably reasonable. And helical wound all metal composite systems can get strengths up to X200. Helipipe here is an example. So this is effectively a metal liner, usually stainless steel, very thin pipe, and around the outside you have a composite system made of steel wires and bonded with epoxy. So the stainless steel on the inside is designed to prevent any corrosion from the product, and the composite on the outside gives you the mechanical strength. Again, very high strength, quite flexible systems if you make them correctly. So they're quite commonly used in things like flow lines and risers. I say quite commonly, there are examples where they are used. But you see the diameter here, this is about 12 inches. They're not used for the very large diameter pipes. These are small pipes, and the flexibility is therefore important. So that's why risers is an application.
But the service life of those, if they're used as a flexible riser,
Yeah.
have they got quite limited service life compared to a typical flexible riser. I mean, it's not going to be much bond strength in between the copper and between the steel binding wires and the epoxy matrix.
Well, you treat the steel wires with an appropriate coupling agent, and yeah, there is a fairly good bonding strength. The key thing with risers is they're not used for ones where there's big wave heights. If it's just a fixed position riser with a small movement on the surface, they have quite long lives. If you've got a big fatigue component, you probably wouldn't use these systems. And the problem is not so much the epoxy side, it's the liner has to cope with all the movements and things, and you'll breach the liner before you fail the outsides. They were originally developed because we wanted to have neutral buoyancy systems for risers, and that meant reducing the weight of the steel in the system, so that the pontoons that they had at the time could actually float them. And there were a few high pressure wells where we needed this sort of material. Are they widely used? No, because you don't need them for a lot of cases. But for very high pressure systems where you're worried about corrosion resistance, this might be the way to go ahead. Okay, so that's what I wanted to say about making pipes. Now I want to say something about fittings before I talk about pipelines. So line pipe, segments of tube you're joining together, that's great. But every now and again you have to go through a bend, or you have to put a tapping point, a T-piece, or you have to bolt a cathodic protection system onto your pipe. So there are things that you need to do which don't involve straight pipe that can be made by the processes we've just talked about. And so we have to make special materials for bends, T-pieces, the flanges for bolted connections, welderlets and sweeperlets, which I'll talk about. And we have to manufacture those processes in order that they can then be joined to the pipe so that they can be welded as anything else. And they can't be made from the same manufacturing processes as line pipe because they're too complicated in shape. So that means that the materials of construction for these fittings are often different from the materials of construction for the line pipe, and the weldability of the fittings is often different to the weldability of the line pipe. So you have to think a bit more carefully about things like that. There are exceptions. You can take a piece of line pipe and bend it in the field, cold bending or induction bend it in a factory, and deliver something which is just the line pipe that you have, but with the shape change put into it. But you can't always do that. For small bends, that's okay, but 90-degree bends, no, it won't work. So we have to think about how we handle the fittings as well as the basic line pipe. So cold field bending happens quite commonly. So here's a piece of pipe, and as you can see from the mud, it is sitting in a rather dirty building site. And we've got a very large system here, and a man is applying a hydraulic jack to the central part there. There's a couple of supports at each end, and they're bending this for a few degrees. And this is okay for gradual bends. So if you've got a pipeline and you want to follow a contour of height around a hill or something like that, you can gradually bend each piece of pipe so that we have a curved path. Because the bend is very small, you don't distort the shape of the pipe, pigs can still go through it, everything's okay. This is straightforward. So it's just like taking a tube and doing that to it, really. It's a very simple bending process. If you bend it too much, the tube will collapse in the middle of the bend, and that will stop things going through. You will also buckle the outside of the pipe and cause quite a lot of damage to the metal, and that leads to weaknesses which you want to avoid. So we don't want to do anything where the bending is too significant, at least not cold. But we have a lot of actual parts associated with pipelines where we have really quite extreme bends. An example, the 90-degree bend here. There's a valve body here. you might have a manifold with things connected. So there's a load of things which do special functions associated with the pipeline, where we have a requirement for things not to go in a straight line or not to be entirely flat. I mean, this area around the valve here, the outside pressure envelope, might be made from line pipe material, but it's a spherical shape, and that doesn't have the same requirements or same manufacturing process. So where we start with a lot of these things is with forgings. So you forge a blank. You take a block of hot steel and you put it in a press and you squeeze it into a mould until it takes up a rough shape. So this would be a flange. This is a flange section to go on the end. And there are small sections of shapes of pipe bodies and pipe pubs here. So these are what you sort of start off with from the steelworks. And then, after machining and after finishing, you'll have products that look like this. And some of these have to be welded on to the end of a pipe. So you've got a bolted flange here, this bit, and this bit here is to allow you to weld it onto the pipe that you're dealing with. So this started off looking like this. And then you've got various sections here with different thicknesses, flanges, different sizes. This is a gate valve, the body of the gate valve. So that's the valve open, that's the valve closed. We have to machine that flat. There's a whole load of things that you have to make that have to withstand the pressure of the pipeline, but are not easy to make from a flat sheet. You might say that gate valve could be, but the other parts definitely couldn't. And they're made from forgings because forgings have better mechanical properties than castings. And they can be big. So this is a rotary forged, high temperature, large flange section, which is to go on a large distribution pipe. So it was forged at 1300 degrees C. It was cooled. It could have, I don't know, for this particular one, it's either normalised and tempered or quenched and tempered, depending on the cooling rate for that particular flange system. And I just wanted to show the size of this, really, for the picture. It's not something that you can easily handle. The crane is there to keep it upright because we don't want to put the other end of it down. We don't want to damage the shape. So you can see where the craning damage might come, as we saw with that shackle in the previous case, these sorts of things here. That's probably a ton of steel. And you've got to have quite a lot of good handling capabilities for dealing with that. You can forge, by having the right sort of mandrel, shaped parts. So you force at high temperatures a billet or a tubular blank into a forging press, and you can make a small bend, a 90-degree bend here, and you can make a T-piece. You can actually pierce a pipe at high temperatures to make that. These are all forged processes. They're hot forged. You have a mandrel, which is something that fits inside, and you force the hot steel to take the shape of that mandrel by the pressure you apply from the press. Sometimes they're made in two parts and seam welded together. Sometimes they're made as a single piece. Sometimes you can't actually forge something that's very big, and you want to bend a large piece of line pipe through an angle that's more than a few degrees, and you have to heat the pipe up and bend it by an induction bending process. These are all possibilities, and they give you slightly different performance, and it depends on really the logistics, the shape of where you've got to put things. You know, sometimes in a piece of plant you only have a small amount of land area, and so you have to have a 90-degree bend because you can't run off into your neighbour's place to give a general bend. So the hot forged bend production is quite an interesting process. So you heat the steel up to 700 to 850 degrees C. and it has to be at that sort of temperature because its mechanical strength needs to be low enough to be plastically worked. So in this case, you've got a high frequency induction coil. You've got a set of tube here, the starter tube that's sitting on the mandrel. The mandrel has this curved shape. You slide this starter tube into the hot zone. It heats up in the induction coil, and it takes the shape of the mandrel. And then what you can't see in this case here is this end of the mandrel, and this end of the mandrel can be just slid out, so you end up with the shape of the bent case. So obviously, if you bend too tightly, you can't get the mandrels out. That's not a good bend. But if you've got a 60-degree bend or something like that, you can have a mandrel design that can be removed. You can break that. The mandrel inside prevents the tube from collapsing as you bend it. I mean, if you take a tube and bend it like this, you tend to find you're stretching the outside and compressing the inside. And the inside of the curve which you're compressing can buckle, it can ripple. And the outside can stretch and break. So you've got to control the process so that you don't damage either side of the tube. And having an internal mandrel helps that. Those of you who've done any plumbing know that a pipe bender for copper pipe at low temperatures has a little steel spring that you put in the middle of the pipe when you bend it to stop this from happening. So this elastic buckling has to be prevented even in these high temperature processes. It's easier, and if you've got very complicated sections, to hot press the segments of pipe and weld two halves together. So this is quite a big one. This is almost a toroid that's being welded. And you can see here, the bottom shell was pressed, the top shell was pressed, and then the welder is just joining them together. So this is like the longitudinal welds that you've got in your line pipe, except that it's curved. Now you can have a submerged arc process that works on a curve. You can set up for doing that. But if you've got something like this, you've got the submerged arc system there, that's easy to handle. You'd only set that sort of process up if you had lots and lots of the same sort of thing to do. So in this case, there was this, you can't quite see it here, this is like a spiral. So this pipe is going to be spiraling along. And it's a very large scale heat exchanger which is used in some processes. That pays you to set up a process. But if you've just got a single bend on a smaller scale, you'd probably do it more with a manual welding process, purely because the economics wouldn't be there for setting up the process on the larger scale. You have to stress relieve these welds and then the whole fitting, so sometimes these have to be put into extremely large ovens and heated to 500 or 600 degrees C to remove any residual stresses from welding. And so this is not a simple thing to do. This is not something you can do in the average factory. There are specialists who are set up for doing this. So to get away from this sort of complex welding of shells together, one process that was invented was the induction bending process. So the idea behind this is we take a standard piece of line pipe that's already been made by the UOE process or something else, and we heat that line pipe up and we bend it in a single process. If we heat the pipe up to a high enough temperature and we're gentle enough with the bending process, we can maintain the geometry of the pipe. So you start off with the pipe on a hydraulic ram here. The ram is right up at this end. And we have an induction heating system here. So you heat the pipe up, and then there's a rotating arm, a pivoted arm here, which holds the end of the tube. So at the start of the process, that pivot is here. The hydraulic ram is completely at the end station, and we heat the end of it up, and then we gradually push that forward with the ram and pull it round with the pivot arm, and the hot material plastically deforms so that we make the pipe take this curved shape, which is dictated by the pivot arm length. Very simple process, in principle quite difficult to get right. You've got to get the temperature right, and you'll notice you're only heating it here, so this pipe's become cold by the end of it. The idea is only a small bit of the pipe is hot enough to plastically deform, and then the rest of it gets cold and has strength increases, and it doesn't plastically deform after that. So you're putting a small plastic increment of bending on each segment of pipe, rather than focusing all the bending in one point. So if I took a piece of paper, which I can see lying around here, I'm going to make a pipe by the simple method. Now I'm going to bend it. You see what's happened there? It's buckled where I was holding it. And it's highly localised, the stresses at that point. If I make a pipe the other way, this is already buckled. Now if I bend that, you only get one of those things. Again, it's highly localised. So whatever size you make the bend, the chances are you're going to localise the stresses and buckle it. By this process, because you only heat an area locally and you're very gentle with the curvature, you're not doing the big change here. You're doing a very slight change and then moving it along and doing a very slight change and then moving it along and doing a very slight change. Then you can get a uniformly bent pipe without all the problems. So that's the theory behind the process, and it works quite nicely. That's one actually being done. So you can see this pivot arm here. See the size of the guy who's the operator. It's pretty small. This is quite a big diameter pipe. You can see the induction heater. You can see that the pipe is cooling in those cases there, and we're just gradually putting it out. And the ram is pushing the pipe from the top in this case. So this is not a small scale process. This is not a field process. This is something that's done in the factory, and then the pipe is delivered to the site. And it's delivered in sections. So this is 1200mm diameter X80 pipe, induction bends being delivered. So you've got to fit them on a lorry, and they've got to go down the road system. So you can't bend 90 degrees easily and put it on the back of a lorry and keep it there. You can. You have the pipe along the length of the lorry and vertically upwards, but you'll take one piece of pipe, one bend at a time, and the logistics costs of delivery are enormous. So you try to avoid having single bend 90 degrees. You could put, these are 15 or 30 degree bends. You can easily put those on lorries and deliver them. More than that, you try not. So we're not looking for sudden bends, we're looking for gradual bends in most of our applications. So we've got to deal with the fact that you've heated this pipe and cooled it. That means that the grain size in the pipe will have changed, it will have grown, which means that the pipe has a slightly lower strength. And you have also to deal with the fact that when you stretch that pipe on the tension side, it plastically deforms, it has a slightly lower thickness. So to maintain the strength in that pipe, we need a pipe with a higher carbon equivalent. So what that's telling you is that we're not having as weldable pipe after it's been bent.
How does that work with overmatching? Are you overmatching the carbon equivalent or the strength of the pipe?
You're overmatching the strength of the pipe in these cases rather than the carbon equivalent. So you want to know what you've got left in the way of strength of that pipe after induction bending. Now, it may be that if you control the induction bending process correctly, that the ends of those induction bends have the same properties as the line pipe, but they will have a slightly higher carbon equivalent, therefore your welding process would have to be adjusted accordingly. The mother pipe's also slightly thicker, so that helps to allow for the thinning of the extra DOS, which is the outside of the bend. So if you're going to weld straight to a piece of conventional line pipe, you've got thick to thin. You can do something in the preparation just to make sure they match up. Usually, I know it says maybe here, but usually there's tangents, lengths of unbent pipe at each end, just so you get good fit up for the on-site welding. You don't want to try and weld just onto a bend in case it's become oval because of the bending process. There are ovality problems though, especially on large diameter thin wall bends. And that may not be a problem, but it may be a problem for pig lines that you want to make sure that the pig will fit through the pipe, even through around the bends. Some people then will take a press, which they will shape, and they'll press the pipe in just to get the round shape back in. It's sometimes referred to as calibration. Really, it's not calibration, it's more reproducing the size that it used to have. And after bending, you have to look at the possibility of high cooling rates that have occurred because the parts of the pipe are not heated. So there's quite a high thermal gradient from the heated areas to the unheated areas, and there's a possibility you could get martensite formation. So you temper them just to make sure that that isn't a problem. So this is another type of thing, another type of fitting. This is a T-piece, and this is a pulled T. So what do? You have a drill, and you drill a hole from the outside to the inside, so you pierce that. You put a rod through that hole, you put a big ball on the end, and then you pull it out through the small hole, and the material plastically deforms to make the extension for the T-piece. And this is often used to create off-takes, and you can do that in the forging process by forging this and extruding material into the T-pieces. There's a whole set of things like that. And one of the problems with this process, see this nice straight edge here on the line pipe, see this rather ragged edge on the top here. You've got to then finish that off if you're going to weld or join other pipes to it. So although this is a fairly simple process for making things, the finishing costs tend to be a little bit high.
Would that be done hot as well? Would it be heated afterwards?
If it's a thick pipe, it would be done hot. If it's a thin pipe and you've got enough support around the outside, you can do it cold. I wouldn't recommend it. Normally it's done hot, 700 or 800 degrees C. Now when you do make a T-piece like that, whether it's a welded T-piece or a forged T-piece, the one thing that you do have to do is check the mechanical properties, and in particular the fatigue resistance of that system. So this is a T-piece which is for the leg of an oil rig, and this is in a test system. So mechanical load, fatigue loading, is being applied to the member on the bottom there, and it's fully instrumented up, you can see here, to measure with electrical conductivity measurements the formation of fatigue cracks on a large scale. And then you have other inspection and test methods that are used at the same time. This is incredibly expensive. So to qualify your fitting for offshore use in particular, you have to do this sort of testing. It's very expensive, and therefore there aren't very many suppliers of fully qualified materials, and they tend to be older materials designs because of the qualification tests. Because line pipe's easy to test and prove, fittings are much more difficult to prove. Sometimes you have to ensure that the shape is maintained and that you have something to keep the structural stability of the system. So this is a guide bar. So these bars in here are designed to keep the rest of the structure in the right position while you put the T-piece in, and keep that in for flow and for use. So sometimes the T's themselves have internal structures. That's one option. But the easiest way to make a T, which is what's most commonly used, is in a two-part design. So you can see these are two forgings that are machined into shape, and particularly if you want to put a T into an existing pipe, a so-called hot tapping, this is the sort of design you'll do. So you clamp those two parts around the existing pipe, weld them all together, and then you can use special tools to actually drill holes in the pipe and put a connection all the way through. Expensive, but if you've got an old asset and you need an extra tapping point, it is used quite a lot. And particularly it's used for repairs. When you've got an asset which is leaking and you want to replace a section of pipe, this is how you can put a replacement in without switching off the flows, which can be essential in some places for costs. Right, so here's an example of a type of fitting that you might want to use in certain applications like this. So this is, you can see here a pipe, and you can see there's a gradual change in shape so that it matches up with another pipe. So this part here and this part here can be forged into the pipe so that that matches up, or they can be welded into the pipe so that it matches up. So sweeperlets, they can be hot forged into the pipe, and welderlets are obviously welded in. And what the difference between a sweeperlet and a welderlet is where this bit weld or this bit weld is put in. So here's an example. So the welderlet, you're welding almost vertically onto the pipe. So we've got that expansion of the shape. So this is the bit that welds onto the T-piece line pipe. This is the line pipe you're welding in. There's a hole here. We've got expanding metal, and we've got the line pipe, and we're just filling in the gap with the welding. So that's a welderlet. A sweeperlet, we're still welding in, but the welds are now in the plane of the line pipe. They're more like the girth welds that we're going to talk about later on. And then the shape is all in the thing you're fitting in. So the welderlet's easy to set up and weld, but it's very difficult to inspect. If there's a crack in here somewhere, it's very difficult to find it with inspection methods. And it involves depositing a large volume of weld metal, the black part there. And basically the cost of welding is proportional to the volume of weld metal you need to deposit, so it costs a lot of welding time. The sweeperlets are much more difficult to set up because you've got to match these things up more precisely, but the welding time is relatively short, small volume of weld material, and it's very easy to inspect. You use the same line pipe inspection techniques that you have on site. So if you can do it, it's best to have a sweeperlet, but the fallback position is the welderlet in most cases.
Would you be more likely to get laminate towering on the welder?
Yes. Yes, it is a problem, and that's why the inspection difficulty makes it more of a problem. So yeah, we'd much rather use this. It's just so difficult and fiddly to get them all lined up, especially on site in a hole in a force 10 gale when it's raining. So I'd say this is ideal, but some people go for the welderlet because it's much easier to do in site conditions. And there are other fittings, pig track closures, valve bodies, and these tend to be made from castings. So the door here, it was actually made from a casting, which is then heat treated and normalised to get the properties that you require. But that means the carbon equivalent will be higher, so they're more difficult to weld. I mean, the take-home message here is, if you've got fittings, they're more difficult to weld. And that's whatever way you look at it, that's going to be true. So fittings cannot be made from controlled rolled plate, apart from induction beds. So they're made by hot forging or hot pressing and then welding. That's the normal suggestion routes. The fittings are normally thicker than line pipe, and that's a design requirement to make sure that they match the mechanical properties of the pipe, because they're made of steels generally with bigger grain size and less alloying elements, or sometimes more alloying elements for strength. They're going to be more difficult to weld, but they need to be thicker to maintain the same load carrying capacity. Fitting steels are more alloyed. So if we look at modern line pipe, the carbon equivalent is 0.3 to 0.4, and the fittings 0.45 to 0.55. So fittings are more difficult to weld. I'll say that slowly, because I think I've seen more problems with people expecting fittings to be welded the same as the line pipe when they're not. And you need a separate welding procedure for fittings for line pipe. Most common fitting is a vanadium and nitrogen containing steel, which is normalised, so heated to 900 and allowed to cool in air. And there are some examples of the steel grades which you can buy to do this. Just so I can, for completeness, those are the concentrations of alloying elements in these things. The table has got smaller numbers in because there are more alloying elements added to give you the strength, so I have to squeeze everything down and fit it on the slide. So that's an indication this is a higher alloy steel, and the carbon equivalent is going to be higher. The carbon content is high. The grain size is fine, but not as fine as controlled steel, so we get that as small as possible by normalising, and then we add the vanadium to form carbide precipitates and a bit of nitrogen, so they become carbonitride precipitates to give us extra strength. So you work harder with fittings to get the same performance. So fittings, as far as I'm aware, are normally limited to X65 grade maximum. For higher strength applications, you have to increase the strength of the fitting, and you can't do that, so you have to increase the thickness of the wall. And generally that means you have a mismatch between the thickness of the line pipe and the thickness of the fitting, so you have to have a gradual change in thickness by putting a taper onto the end of the fitting. So 1 in 4 taper, 14 degrees, and it's made at the weld preparation stage. And generally we say that this difference in strength of thickness shouldn't be more than 1.5, otherwise you'll have a very, very long taper, and that will be very bad news. Failure will occur in the taper, and we don't want to do that. So here's an example of a weld preparation. So this is the normal V preparation at the end. So this would be where the root is, that's the root face, and the root gap would be here. This is the normal V preparation. But the fitting is bigger, so we've got this taper here and there to increase the size. And that's a relatively short distance. It's comparable to or a little bit larger than the thickness of the plate. So that's in the area where we consider as part of the weld. If we made that taper too long, you'd have part of it that's outside the welded zone and wouldn't be really good, because the defects might be introduced there in the plate manufacturing and the forging process, which is not what you want. Toughness requirements: the fittings are thick. Generally, they're spaced in frequently along the pipeline. So generally, in a fitting, fracture propagation is not an issue. If the crack runs along the pipeline and comes to a fitting, it tends to stop. What we don't want is the crack to start in the fitting. And so for that reason, we just tend to use a fracture initiation criterion as our design requirement, like a Sharpie test nut. Usually, as I said, it's specified at the minimum design temperature, and there are absorbed energy requirements based on good pressure vessel practice. So there are standards that are available for doing this. British standard 5,500 has been superseded now, I know, but there are more standard pressure vessel designs where you can use these fitting materials and where you can look at the Sharpie data that you need for them. As a rule of thumb, if you take the energy requirement for the Sharpie test in joules, take the minimum specified yield stress, divide by 10 in newtons per millimetre squared, and that will give you the energy requirement in joules, roughly. And that's what a lot of people in the industry use. They just take the numbers and divide it by 10 quite easily. So, what I've said here is that fittings are not the same as line pipe, and that their strength and toughness can be adjusted by composition. What I will talk about at the next lecture next week is a little bit about the weldability of fittings, and then we'll go on and talk about actually making a pipeline out of these pipe elements and the fittings that might have to be used. And as I say, the take-home message is don't regard fittings the same as pipe. If you know that, that's a good first step. Okay.